For a problem like Cantor's disappearing table, it can really help to be organized with the table. So I'm going to start with iteration 0, where it's the entire table, just one slat of wood, nothing's been removed. The total length is 1, and the width of that slat is 1. When we remove a quarter, the way it describes in the picture, for the first iteration, then there becomes 2 slats. And then this becomes a real easy column because we remove a quarter, then an eighth, then a 16th, and a 32nd. At the nth iteration, we've removed this much total. This is also easy. When you look at the pictures, there was 1 board, then 2, then 4, then 8, then 16. So those patterns are easy. And we can answer this question right off the bat. How much total table was removed if we've removed a quarter and then an eighth and then a 16th and then a 32nd? Well, that's just a geometric series. It converges because the common ratio is just a half, which is smaller than 1. And the infinite sum is the first term divided by 1 minus r, which is 1 minus a half or half. So you can see that we can do this forever, and we will converge to there being 50% of the table at the very least. So the total length removed in this infinite process is 50% of the table. Half of the table remains. Now, why does it become invisible? Well, if we look at the width of each slat is 1 in the beginning, and then when we remove a quarter, there's only 3 quarters left remaining, but there's 2 slats, so 3/4 divided by 2 slats is 3/8 per slat. And then when we remove another eighth, there's only this much remaining, but there's 4 slats, so each slat is the width remaining divided by 4 slats, which is this much. And we can quickly establish this pattern, which is this expression. And as n approaches infinity, that expression approaches this expression, which approaches this expression. And as n approaches infinity, that approaches 0. So the width of all the slats approaches 0, which means it becomes invisible, even though 50% of the table remains.